Good day, ladies and gentlemen, and welcome to the rest of chapter 12. All right, so let me see here. Let's start with a screen share. And we were somewhere, I forget where this was. I think it was page 99. So if you want to have page 99 bookmarked for today, that's kind of the, we talked at length about this last time, so I don't want to go over it again. Whatever. All right. And so just remember this is here. The big thing that I kept telling you, draw pictures, do torques first, and you could choose multiple pivot points if you want to, because it's not rotating about any point. All right. So that said, we did a couple of these rod problems. And one thing that we did a bad job on was cylindrical geometry. So I want to look at this one again. In particular, let's focus on the spherical object, or this object that has some sort of circular symmetry. And let me get this over here just so I can see it better. All right. And so I'm going to make this a little bit bigger. And I want to focus on just the object here. And this is problem, sorry, I forgot to say that, 12.8. This is problem 12.8 on page 103. All right. So one of the things that's tricky about these circular objects, and once you get used to this, it's not too bad. The normal force points perpendicular to the surface. With this plank, for example, this would exert normal forces either that way or this way, right? Perpendicular to the surface. However, here it's not so obvious. Spheres are going to exert normal forces radially outwards. So if you rest something on a sphere or a cylinder, the normal force is going to point directly away from the center on other objects. As a result, by Newton's third law, there's a normal force directly towards the center from the plank. And so now, just so I could clear all this junk out, the thing I wanted to stress here is that normal forces are going to go radially inwards here on the ball. So we could call that normal force B. Similarly, the normal force at A is going to be radially inwards. Now, I know we alluded to this last time, but I just don't want that fact to be rushed. Is everybody okay with that? This turns out to be somewhat useful because notice, if you pick the center of mass of the ball as your pivot point, three forces drop out. What are the three forces that drop out on the ball?
The normal forces in mg.
Mg. That's the other one that I didn't draw, right? And so now here's something else that we could think about. Let me do this. Turn this up a little so I could hear you better. My volume was way down. Sorry about that. Okay. There's also frictional forces. And now maybe it's not obvious which way these frictional forces go, but I'm thinking of this ball as wanting to fall down. So I would think friction with the wall would tend to be upwards. I could be wrong in certain cases. I don't know. But this seems logical to me. All right. Questions about that frictional force? Notice from our old knowledge of chapter 6, the frictional force and the normal force are perpendicular to each other. We see this right angle. We see the friction is parallel to the surface of the wall. Notice that turns out to be tangent to the surface of the circle. So when we have circular objects or objects with circular symmetry, we expect normal forces point radially inwards, and we expect frictional forces point tangent to the circle. Now, imagine we want this ball to be in static equilibrium. Which way does friction point on the plank? It's either going to point up the plank or down the plank, so to speak, towards the pivot or away from the pivot. Which do you think is correct in this case? Which way should friction point it be?
I'm gonna take a guess. I'm not so sure, but I will say up the plank.
Yeah. One way to tell is if this ball is in static equilibrium, the forces should balance. But when I look at this, this is not immediately obvious. There's forces all over the place. An easier way to see it is do sum of torques about the center. If we do sum of torques, I'm going to call the center point C, okay, just because C for center. If I look at the point C, we've already discussed that NA, NB, and MG cause no torque. Look at the torque due to FA. That's going to rotate it this way. You could call that a positive torque or a negative torque. It doesn't really matter. But it's really easy to see that the only way this is possible is if this one is exerting a negative torque. Now, again, you could argue, should I make these plus or minus, flip them? All that matters is I chose to call this one positive for no good reason. It was just the first one I chose. I picked the first one to be positive. If you're a math purist, maybe you would want to say the other way, like this. You could have said this is the positive torque because it's going out of the page, so to speak, and you could call this the negative torque. But the fact is these two torques have to balance. Notice the following piece of information. What's the lever arm for this torque? Right there. At B, what's the lever arm in this case?
Just radius?
The radius. And does everyone agree the other one has the same lever arm? I hope you could see that. We have the same lever arm for each torque. So if we need these two torques to balance and their lever arms are the same, what does that tell us about FA and FB?
They must be equal in magnitude.
Yes, exactly. And so that's what tells us this frictional force has to balance that frictional force. Now, here's an interesting thing. As soon as I tell you that, do you think this thing is on the verge of slipping? I would guess. Oh, go ahead.
I was going to say, I don't think you can tell, can you?
You can't tell, but it's almost impossible for it to be on the verge of slipping at both points, right? What are the odds that this normal force exactly balances that normal force? 0. This one's only in the X. That means the X component of this normal force has to balance from forces. Agreed?
Okay,
So,
No.
yeah, so there's no chance that this thing is on the verge of slipping at both points. Again, we see that NA has to equal NB in the X component only. They're the only, well,
So-
actually, maybe not. I forgot there's an X component of this one.
Maybe
So the plank would have to be completely horizontal, right?
It would have to be just right. I misspoke there, Esteban. Look at this. There's an X component of both the normal force and the friction B. So, but the odds of this happening to work out just such that the two normal forces are exactly equal and both on the verge of slipping seems a bit unlikely to me. It's not impossible. It could be at a certain angle that is the case, but I don't know what angle that would be. Maybe it's true at all angles, but it's not obvious, and I don't really care. But I just wanted to point out, I would not be quick to think this thing is on the verge of slipping. That's all I'm saying. Nothing in the problem indicates it's slipping, and my logic here seems to say, it seems like you'd have to have a special set of situations just to make this thing be on the verge of slipping at both points A and B simultaneously. More likely what happens, it's on the verge of slipping here and it rolls out like this, or it's on the verge of slipping here and rolls out like that. Who cares? All right. Let's take a look at the solution and see if there's anything about this one that I wanted to. Basically, I just wanted to practice the FBD. So I did not actually want to solve anything. It was just sketch the FBDs. So technically that was not an FBD. I drew the forces on the object. What was this, 12.8? So there's the FBD of this thing. Ooh, I accidentally called C a different point in the solutions. My bad. But if you can draw the force equations, I hope that you agree you could get the, if you could draw the FBDs, I think you could get this calculation right here. And then here's forces on the plank. And again, I'll focus on one particular piece of this one. Notice these forces are flipped because of Newton's third law. The plank exerts forces on the ball this way. Therefore, the ball exerts forces on the plank that way. These are just some random forces in the pivot. I didn't think. I just said CY points up, CX points this way. When you look at the FBD, which of the reaction forces, CX and CY, is probably going to end up being negative number?
CX.
Yeah, look at this.
Yeah.
This has an X component this way, so CX had better turn out to be a negative number. This is not a problem. I drew it this way. To the right with a negative number still makes sense. So that's what I'm alluding to right here. We expect, look at it right here. This is a positive number. This is a positive number. CX is going to have to be a negative number. All right. All right. And that's okay. Notice it points opposite the direction I drew it. That's what that means. All right. Any questions on this one while we've got it up? Just practicing writing the forces. That was it. Now that we know how to do that, why don't we see if we could do a problem with this type of geometry that matters? I like this one. This was 12.11. I think it's on the next page. Let me check. 104. Suppose you're a civil engineer and you want to make sure people in wheelchairs can get over the curb, right? That would be nice so that people could actually navigate your streets if they're in a wheelchair. This is a reasonable thing to do. Our goal here is to figure out how the forces that the person must exert relates to the curb height h. So we're learning about height h based on reasonable assumptions of a human being. Obviously, you would put in a ramp, Esteban. That would be your first goal. However, in certain situations, maybe you also want to make sure, what if they don't see the ramp, right? Maybe you want to make it so that they could easily get up the curb height as well, given reasonable assumptions, right? The ramp is clearly a better way to go, but what about between ramps? Because you can't afford to put in ramps everywhere. It's expensive. So, but we could do something where we keep the curb heights low enough that a average wheelchair user should be able to navigate even a small curb. Again, for those instances when a ramp is where you're between ramps or something. Do you agree? Hopefully that's hopefully you think that's a reasonable proposition. Let me see here. Yep. Okay, so let's assume the person could put in this much force. So, right, they're going to apply that force to each wheel. The radius of the wheel is R, and then the person, the chair, and all of their essence is just has total mass M. And let's say we did the math and figured it out. I hope you agree the center of mass would not be at the center of the wheel because the person's body is going to raise it up somewhat. Now, obviously, the wheels are going to keep it low, but the person's torso and their head should raise the center of the mass slightly above the center. That's what that's supposed to indicate. Instead of having the center of mass right at the center, sometimes the center of mass of this system might be slightly above the center. Okay, that's what I'm trying to model here. So notice rather than being distance radius above the ground, it's slightly above it. Let's say it's 20% higher. So 1.2 R above the ground. Okay, so we want to determine the maximum height h. So we're trying to figure out h if the person can get over the curb. So we're going to make an assumption about how much force they have and then see, okay, what's the tallest curb I could create for a given amount of force? This could help a civil engineer design a curb or a step. All right, now think. This is indicative of a general class of problems that's a little bit weird. I want you to note this fact. This is a big deal. Okay, if the wheelchair just barely lifts off, where is it rotating? Where is the pivot point?
Can you say the pivot point is the corner of the curb?
Yes, that's the obvious pivot. So the idea is they're going to be rotating about this point with what value of alpha approximately if they're just barely able to do it?
0.
Yeah, alpha is approximately equal to 0. So obviously, any value of alpha greater than 0, the person would start going over the corner. Okay. That's what we're trying to do here. So we're going to make this set of assumptions. Is it perfect? No. But does it get us a pretty good estimate for what might be required? Absolutely. Now remember, if we go at this minimum value to lift off, alpha is effectively 0, so statics is approximately applicable. So that's the trick to doing these things. You say, I want it to rotate, so I find the cutoff value by setting acceleration to 0, sort of like we did in on the verge of slipping. We would set acceleration to 0, and you could solve for mu static or normal force or something. All right. I don't know if you've already gone to the solutions or not, but hopefully not. If you haven't, try and draw the FBD. And we could talk it through as a group, and then we'll go to the FBD itself. I'm going to make this big. Get over here. What's one force acting on this?
The obvious one is mg at the center of mass.
All right. mg. What else we got? Anybody else?
Normal force going up
From where? Now,
from
at
the
what
bottom
point?
of the wheel.
Okay. I'll call that normal force little n here. What else do we have? Is there going to be friction associated with that normal force? Maybe we're not sure. If there was friction, which way do you think it would point? Think about this.
I would say towards the left.
Okay, which way is the person trying to rotate the wheel? They're trying to twist the wheel this way. Do you agree? They're trying to twist the wheel that way. Are you okay with that?
Yeah.
So which way would friction work to oppose that?
To the right.
Yes. Isn't that weird?
Very confusing.
So think about it. The person's trying to make the wheel, the bottom of the wheel, go backwards, so the top of the wheel and the center of it go forwards. So there's friction to oppose that. The friction is the force that makes the wheel go forwards, right? Think about it. The person tries to make the wheel go backwards. As a result, the earth is trying to friction against the wheel in the forwards direction. Even though friction is not a verb, I think it makes sense here, right? It's trying to friction the wheel forward. This is why I'm like, if you try to walk on ice, you have trouble going forwards because you don't have enough friction to push you forwards. Okay. Now, what's another force here? If it helps, go ahead.
Isn't there the R force on the pivot?
Okay, the reaction force.
Yeah.
Now, in this case, there's not an actual pivot there. So what types of forces occur at this pivot point?
Normal forces?
Which way does the normal force point?
Perpendicular to the point,
Yeah, but is that this way or is it that way or is it both?
like radially inward.
Probably right towards the center, right?
Yeah.
So let's draw that. We'll say there's a normal force here. Let's label them later, okay? Like 1 and 2. Let's not do that right now. Just give me a second. What else might be present there?
Don't go that way.
Friction as well.
I'm stuck.
Friction, and that probably points this way, right? Now, in this case, you could call this, sorry if that's hard to see there. That's a letter F there. Oh, geez, that's a bad idea to draw that arrow. There's a friction there, and I've got this picture in the solution manual, so don't worry, we've got it drawn better in there. But the normal force does not go towards the center of the mass. It goes towards the radius, towards the center of the wheel, right? Radially inwards. Now, you could also choose to call this something like R radial, and you could also call this one R tangential. And that would be effectively what Christian just said. Do you agree? Now, I think this set, rather than calling them Rx and Ry, you could say maybe this is a good idea. And in the end, who cares what we call these? Why is it not going to matter in the end what we call these two forces here?
Because they're not going to count.
Yeah, they're going to drop out if we do sum of torques about the pivot. And then if we did sum of forces, we could figure out whatever we wanted. So to be honest, Christian's suggestion of calling them just Ry and Rx and not thinking about it probably would have been even smarter than what I was suggesting here, right? Because these forces don't matter by themselves, and you could still figure out the net force at the pivot later. All right, have we got all the forces? I think there's the force of the hands. Each hand exerts a force F. So there's an F from one hand and an F from another hand. I think that was all the forces. Now, we know that these forces at the pivot don't matter. My claim is that two other forces won't matter at all either. Which other two forces don't matter?
Normal force at
Why?
the bottom.
Why?
Because it's lifting up.
Yeah, if it lifts up, what happens to the normal force?
Goes to 0.
It goes to 0, and if it's not touching the ground, there's no friction. So in this particular case, really all we need are those two. Let's go to the solution here and show you what I mean. And apologies if I took too long to get through that for you. What number was that? 12?
12.11.
Oh, thanks. There it is. So this is the tricky part. And I forget who that, it might have been Jose that was talking about the normal forces at the bottom. Look, I screwed it up, Jose. Do you see it? Huh.
Oh yeah, I see it.
See, so now I just focused on the fact that they're set equal to 0, but I should really fix this up and make that arrow point the other way. But I knew it didn't matter anyways because they're not making contact, so I didn't bother to think about it. So that's a bad job on my part. But does that make sense why the friction points the other way now?
Yeah, it makes total sense.
Okay. Now, in this one, if we looked at this and I read these words, sum of torques, I know I need to do sum of torques. This is the obvious pivot point to choose. So these two forces drop out, line of action through pivot. These two forces drop out because it's lifting off. What method would you use to solve this problem? Would you do lever arms or how would you do it? Or would you try and do R vectors or what are your thoughts? And let's be honest, there's different ways to do this and they're all correct. But I want to point this out. This is what screams out to me. I see two forces that are easy to draw lines of action. That's an easy line of action to draw. Do you agree? This other one over here, that's an easy line of action to draw. I think this problem is screaming out for lever arms. I just need to get this distance right here. That's one of the lever arms. That's going to be R perpendicular for mg. And then I could see I need this distance here, which actually I already know. I could just look at it and tell that's going to be 2R minus h. Do you see that? Everybody see that this one is 2R minus little h? I know the total distance right here is 2R. I know that this distance right here in the picture of the problem was h. I'm going to pause there. Does that make sense? Or am I losing you?
It makes sense.
Okay. So to me, when I see forces going straight up and down, left and right, man, that's like screaming out for a lever arm. The hard one is going to be R perpendicular for mg. Do you see that? But we do know this distance already. And so now the question becomes, if I know this distance, give me a second. I'm adding a new purple line. I don't know if you could see it yet. What's this distance that I'm pointing to right here with the little arrow?
R.
Yeah. So now, do you agree? We basically know one side of the triangle, another side of the triangle. Shouldn't you be able to get this side down here, this R perpendicular? And that's, let's scroll down and look at it. That's what I was doing right here. So once you do that, the problem goes pretty quickly. It's kind of ugly, but look at this. This is another trick. Oh, I just realized I was slow to add Deanna there. Deanna, sorry about that. I was writing and I didn't see that you needed to add. My bad. All right. Sorry about that. But this is a classic technique to make your answers look prettier. You get some big ugly mess like this. And then what I did is I'm like, you know what? This thing's ugly and it appears all the time. I'm going to say that is just some constant K. It's going to equal 2F over mg squared or whatever. And then it's easier to do the algebra because I don't have to keep writing that over and over again. So then I solve the answer using this parameter K. It just makes less work for myself and specify what that parameter is. So that's a style of doing this problem. You could argue, are there other ways to do it? Yeah. Could you use the quadratic formula? Probably. But this particular one, we don't even need the quadratic formula. So what do you think?
A lot more convoluted than originally I thought.
It's surprisingly sneaky. Yeah. At the same time, it's like, this is the easy part, right? You're like, you could probably see that almost immediately. And then the issue is in the geometry. It's all geometry to get the problem done. So just because the concept is easy, now that you've seen how to deal with circles, these are the types of issues that show up with the circles. And so we've done triangles with boards and planks, and now we've done some circles. Let's try one more with circles before we go on. All right. Let's get back into here. Sorry. Oh, this was a problem I thought it'd be pretty straightforward. I put it on a test, kick the crap out of people. Let's focus on drawing the FBD because I'm confident you know how to do algebra. So read this problem. And I'm going to give you a minute to try the FBD. Tell you what, I'm going to get a glass of water. Try to draw the FBD without looking at the solution just to see if you can get it. And then we'll know that you're starting to get this. All right. So not sure if I gave you enough time here, but in this case, what are some of the forces? What is a force that acts on this? Anybody? I'll do the mg.
Yeah, tension where the string is or where the wire is.
Okay. So we'll color those red just for no good reason. So let's say the tension's here, and I'm not drawing these arrows to scale. Sorry about that. I'm drawing them whatever makes it easiest to label. What's another one?
Yeah,
Is
normal
there-
force. Oh, sorry, go ahead.
Oh, no, go ahead. No, I was gonna say friction to the left at the bottom.
Let's see. Friction to the left. Let's see. Is that right?
I would say friction to the right.
Let me think about this one.
Doesn't
As
it
you
spin?
pull, you're trying to rotate. Now, if you pull up this way, do you agree this thing's going to try and rotate that way? And that means we're trying to spin this thing that direction. Friction should oppose that. I think friction points the other way.
No, I thought it was
Lot of-
spinning counterclockwise.
So if you lift up, do you agree it would probably spin that way?
Yeah.
All right. And so do you see that's one of the hardest parts about these circle ones is which way friction points. You know it's tangent to the circle. So in both problems, we've had to kind of think this through, like which way would it tend to spin, and the frictional force opposes it. All right, so let me clean this up a little bit. All right, so there's friction that way. And I assume you're good with there being a normal force towards the center here. Sorry if that's hard to read because of the colors I chose. Any other forces or not?
Oh, on the wall to the wheel.
Yeah. So the wall is going to have similar normal force and frictional force. And so because we're not sure, we should probably label these. We could label the ones down at the bottom 1, and we could call this one 2 or whatever, something like that. So there's the FBD. If you were going to do some of, oh, go ahead.
I was gonna say there's no friction between the wall and the spool.
Is that right? Is that what it says somewhere? Where does it
Yeah.
say that? There is negligible friction. Nice. So that means this one goes to 0. Sweet. Thank you. That cleans it up a little bit. Okay. So if you had to do sum of torques, where would you do sum of torques in this problem?
You would make the center of the wheel the pivot.
That looks good to me. Which forces cause 0 torque about the center?
That would be mg in both normal forces.
And then now we have 2 forces. You could do a sum of torques and you get it back down to 2 problems. Why is this one a lot easier than the last one?
The geometry?
Yeah, what's R perpendicular for the frictional force?
Just radius.
Big R. What's R perpendicular for the tension force?
So I was thinking T sign.
Nope,
No.
R/3.
just R over 3. This is what's cool about pulleys and strings. That is perpendicular. Do you agree? The radius is,
Okay.
and so you start to think it has to be complicated just because now the angle matters for doing sum of forces. Do you agree?
Mm-hmm.
So you're going to get, so to be clear, let's go to the solution. That's the trick on this one.
So I was trying to split up the force vector.
Yep.
Okay.
So now you could do that. Deanna, I'm sorry I'm slow to add you every time because as soon as I'm drawing, it covers up the add button and I just didn't see you there. So I apologize. That's twice. I'm not trying to leave you out. I just screwed up. All right. And this is what gets people. It's that lever arm right there. Right. If I could draw this perfectly, that is pretty close to perpendicular. And you can see it. And then similarly down here, there's perpendicular. What matters, you do need the sine and the cosine for the force equations. Yep. It's all about getting this. Have you noticed that? Once you get to this point, it's easy. It's algebra. Well, I wouldn't say it's easy, but it's algebra. Obviously, algebra requires practice like anything else. Is everybody okay with this one? I listed some assumptions down here. We were told there was negligible friction between the wall. That's why there's no friction too. And then we're told it doesn't lift off in the problem. That's why N1 was not 0 for this problem. In the last problem, you're told the wheelchair is getting over the curb, so it does lift off. So that's why you could see the types of things that show up. And now this is basically all of my tricks that I think you've seen, maybe with one more. I'm going to stop for a second. What do you think? So far, so good? All right. Let's do one more. There's enough tricks here. It's worth doing one more. Okay. So this one was an exam question that killed people. Some of these other ones are exam problems that killed people. So a lot of this chapter is basically, this was an exam problem that killed people. I'm going to let you do that one on your own. This is one I was thinking it'd be pretty easy to simulate. We'll talk about that later. This is a classic problem in every physics book. Ooh, I'm going to come back to this fictitious forces. I wanted to show you one other one. This one killed people. This was another test question that just destroyed people. You got this sphere, you've got a cable. The angle is alpha above the horizontal. Oh, the incline is angled alpha, whereas the string is angled beta. Oh boy. And the cable goes radial away from the center. All right, we could see that in this particular problem, you didn't even need to do sum of torques, which is an odd problem. It's basically pure geometry. Let's make sure you understand the geometry here, right? That's what's hard in this problem. Okay, so let's kind of go through this one. How do we figure out the angle alpha? Any ideas? What was the trick we learned last time when you have triangles that are not right triangles?
make them into one big right triangle.
Make right triangles. Okay. There's two right triangles. Is there any angles that we know? Obviously, this is a right angle and this is a right angle. We know alpha and beta, I believe, right? How do I get gamma?
Well, the corner on top of the ramp is 90 minus alpha,
Yep.
and then you can add that to beta, figure out the difference from 90 degrees. I
You're
know.
on it. That's it. So this angle right here would be 90 plus beta minus alpha, so to speak, or you could rearrange it differently. And then what Esteban's saying is this angle plus this angle plus this angle equals 180, and solve for it. And that was the trick in this problem. Everything else is geometry, or I mean, just forces. Does that make sense? I'm not trying to kill you here. It's just that geometry is a big part of these problems. Can you guys follow that logic?
I'm interested to know why torque doesn't apply.
You could use torque, but you don't have to. That's the deal in this one. Should we look at it?
What are we trying to solve? I haven't.
Oh, I
Sorry,
have no idea. Yeah. So to be honest, a lot of times this is I don't know if you noticed, this is my strategy. Figure out the geometry first, then read the problem. I just spend a little time playing with it. Let's actually read this problem now. Okay. So what was the point? First it was figure out this angle, and then what do we figure out the tension in the cable? So we're ultimately trying to get the tension in the cable. Okay. So that said, I hope you agree that basically if we know alpha and beta, we also know gamma. Are you okay with that, everybody? If alpha and beta are givens, I could figure out this one. And then from that, I could figure out this one. I'm going to assume that's okay. So what is one force acting on this particular object?
So you have tension, mg, and normal force.
Okay, so we've got tension. Let me do this. There's the tension. We've got which weight is mg point? I guess straight down. Let me get a different. I'm just going to stretch this big just so I can see it better, okay? Sorry if this doesn't draw into scale. And then just so I could see the last one, let's do this. Like that, right? Now, were we told there's negligible friction in this problem?
Yeah.
Okay, so that's why there's no frictional force. There's negligible friction, so we got an N. Sorry for the screwed up sizes, not to scale. There's mg, and then there's the tension. Now, in this case, if tension is given, or sorry, if mg is given, I think what happens here is this. If I draw all these forces on a different spot, there's an mg down, and then there's a tension up this way, and a normal force going the other way like this. Not necessarily at right angles, right? In this case, couldn't you do sum of forces, two equations, two unknowns? That's what I was trying to get at, why you don't need torques. Does that answer your question?
Yeah.
Yeah. Now, maybe it would be smart to do sum of torques In fact, if you're trying to get the tension, why is doing sum of torques a good idea? And which point would you choose? If you're trying to get the tension force out of this problem, where would you choose the pivot point?
The floor.
Yeah, that drops out n. You get one equation and you're done much more rapidly than if you do all this crap. That said, we are so good at doing this crap, I discovered that tons of students just did that. And I'm like, oh, okay, that's cool. You solved the problem. Full credit. That wasn't what I was expecting people to do. I thought they would do sum of torques because it makes it even easier. Now, this is where it gets a little bit tricky. What's this angle in here? Between the normal force and mg. What's that angle?
Is it gamma?
Let's take a look here. So this is 90 minus gamma. And then let's see. So this angle over here would be gamma. And yes, you're right. We're seeing it's the every other one. So notice in this case, it's gamma that we are caring about, not alpha. In so many problems, we were always just taking this angle and shoving it in here. And I wonder if that's why everybody screwed up this problem on the test. So we see that you have to pay attention in these problems. Sometimes there's like, it seems like no matter what I do, every problem has some little trick that if we go nice and slow, you catch it right away. But if you're trying to rush through this chapter 12 problem, you can get ruined by a subtle trick if you're not paying close attention. And maybe that's what's so deceptive about chapter 12. It's easy stuff. We've been doing forces for months or years now. And then you're like, torques, okay, I kind of got that from chapter 10 by this point. But the angles get you. All right. So far, so good. Let's go look at that one. I forget which problem that was.
18.
Okay, thanks. So I tried to draw a bunch of different ways to see this one, and I drew some different pictures here. So hopefully this helps you kind of follow through all that junk here. Oh, weird. There's some, ooh, the torque. There, this is, look at these angles in here. So it looks like I worked this problem out using an alpha. So wait a second here. Let's see if I had this, I might have drawn this picture differently than we drew the last one here. So let's check this one out and see. We may have all just, I think I just screwed up a second ago. So this is why you check the solution. Okay, let's go through here. Alpha, alpha. All right, so if that's alpha, this is 90 minus. So this angle inside of here, actually, it is still alpha. Maybe we drew a different one on the last one, or maybe my picture was sloppy. I don't know. But look at this beta in here. So it looks like gamma is not used at all. And maybe that was just the way I chose to do it in this particular problem, right? Notice what I did is I picked a perpendicular distance here. If this is beta, and if this is a right angle, that makes this 90 minus beta. But I know that angle's, oh my gosh, look, this is sneaky. And I just screwed it up a minute ago and I wrote the problem. So clearly these problems, there's some geometry that are sneaky. Big pictures help. That's all I can say is big pictures help. I don't know what we screwed up on that last one now. And who knows? Maybe if we do the math, maybe that other method was also correct. I don't know.
I don't think gamma, there's no way gamma can equal alpha though.
I don't think so. What was it? It equals alpha minus beta. And maybe because beta is such a small angle, I didn't notice it in the last picture. So, oh, look, I even did this one a different way up top. So I said, if this is alpha, supplementary angles, and then I got right into here and then did the angles in the triangle. All right, so moral of the story is watch out for your angles, draw big pictures, get the angles right before you waste time doing these. And look, even that picture, I drew it even bigger with the forces on it. I think that's enough said on that. All right. What are we learning here? Chapter 12 is deceptively tricky, and it's all about the angles. All right. The geometry is what gets you. So spend the time practicing the geometry and fighting through these. And to be honest, I can't imagine giving you a question on a test that isn't already in here. For like a couple years in a row, I happened to pick a question that just kept stumping people, and I just kept sticking them in the book. And so now I think you could see all of my tricks in the book, but just don't underestimate chapter 12, even though it's the easiest sounding chapter. Sum of forces equals 0, sum of torques equals 0. So far, so good. All right. Now you're probably hankering for a break, but I want to do one more problem before we get to the break. All right. And I don't want to explain why right now. If you're curious about tipping problems, here's a problem where we talk about tipping instead of slipping. If you're thinking about this, you could think about where does the normal force act on the block? If it's going to tip over, where's the pivot point? I'm looking at this block right here. If that block is going to tip over, where is the pivot point?
Lower left corner.
Yeah. So that's where the normal force acts. We've always been drawing the normal force right in the middle. That's not in general true anymore. The normal force is going to act right here. Got it? And so I don't know if you could see this. Let me just make this bigger. Let me go one bigger. The idea is things are going to tip over. Like imagine this is a box you got from Amazon and for some reason it's high center of mass, okay? What do you notice about mg and the pivot point for this particular problem?
No torque.
No torque. Now, anytime the line of action for mg exceeds the pivot point, it's going to tip. So, and to be clear here, there's got to be friction that's holding it up the ramp too. So if you're worried about things tipping over, generally speaking, if the center of mass is high up, it's easy for it to tip over, right? Because it's easier for the line of action to get past. If you get this line of action, if this was just a little bit higher like this, sorry, it's not perfectly the same size. But now in this case, if we draw the same mg force, notice the line of action has a lever arm and you get a torque from mg in this case. So if you're thinking about things tipping over, try to think about where the center of mass is and think, is it going to cause a torque that causes it to tip or not? Obviously, if mg was over here, that would serve to keep it on the plane rather than tip over. But anytime basically the line of action from the object's center of mass goes right through the pivot, it's on the verge of tipping. Okay, that's one thing about tipping. The other thing is, how did it get from 10% to 20% these days, you know? Oh, well, that's just it's probably because our society is not set up for people to, it's kind of a weird system. All right, whatever. That's a whole nother ball of wax. Now, this is the problem I actually wanted to spend time on briefly. We don't usually do fictitious forces. So I'm going to do a quick review of fictitious forces. Remember, let's say you have a block like this, and let's say you're pulling it this way. And let's say there's a normal force, and let's say there's mg. If you applied these forces, Do you agree the block would accelerate this way? Nothing crazy there. It turns out you could actually draw this thing as a different FBD. You could say there's a force the opposite direction with magnitude MA. And the other forces are still present, N, F, and mg. The idea is what we're doing is we're doing a mathematical equivalence. And in this problem, you say that A is equal to 0. These two FBDs, the left one and the right one, would produce the same force equations. Because you have sum of forces equals MA, well, the sum of forces minus MA should equal 0. At first, you may say, this is stupid, dude. Aha, here's the reason you do this. If you have your net force equal to 0, you have a statics problem, and all the tricks of this chapter apply. If you want to know when the car will tip instead of slip when you're driving in a circle, you could do the following. This car is driving. There's a, let's say its center of mass is right here. There's going to be an mg force. Now, if this is going to tip, well, let's first describe which direction is this car accelerating in this picture. We got a car. Let's read this problem. You got a car. It's going around. This is the center of the turn. I know its mass points straight down at the center of the vehicle. Which direction is this thing accelerating?
AC towards the center.
Yep. So where is the fictitious force?
So MAC pointing the opposite direction.
And then we could say A equals 0. Which way is the car going to tip? Will it tip towards the inside of the turn or the outside if you had to guess?
Outside.
So where is the pivot point?
On the right tire.
There's your pivot point. You've got a statics problem. You could say this torque equals that torque. Now, obviously, I'm circling force magnitudes here. I should technically say the torque due to this fictitious force must balance this torque if you're at the onset of tipping. And so this could tell you what speed will cause you to tip. Also, we could see some differences here. What advantage is it to have a low center of mass? Let's say you had a lower center of mass right here. Or let me draw that again. Let's say the center of mass was lower. What happens to the torque caused by mg? Does it change? Does it increase? Does it decrease? Does it stay the same? If I use a lower center of mass, does the torque due to mg change? And if so, which way?
It doesn't, right?
It doesn't. The lever arm stays the same. What about the torque due to MAC?
It has a smaller lever arm.
Smaller lever arm, it's less likely to tip over. So the lower your center of mass, generally speaking, the less likely you are to fall on your face or tip over your car or whatever. All right, we still got 30 minutes. Let's take a short break because I bet I'm kicking your butts right now. But before we do that, any questions about this stuff? It's exciting. I don't know. For stuff that's not moving, it's pretty cool, in my opinion. All right, let's take a 9-minute break here. All right, 9 minutes. So on my clock, I've got 1:46 on my clock, so we'll come back at whatever, 1:55, and then I'll close with a few details. I'm going to stop the live stream now and start a new one afterwards. That's why